Hey, morning all! Welcome back to another round of astronomy. Yeah, let's get going. Last bit of physics that we are gonna discuss is this idea of energy. Okay? Now, I know your book doesn't talk about it. I find that it's easier to discuss some of the phenomena that occurs later in the course if we have this idea of energy rather than talking about forces. Okay? Usually, if you're talking about forces, you'd have to discuss things like pressure and volume and ideal gas law and blah, blah, blah. No. I prefer to think about it in terms of energy. And specifically, we're going to give you two forms of energy. Okay? One that deals with the motion of an object, and one that deals with the how far an object is above the Earth, for example, a gravitational center. Okay? And so with those two, I think that we'll have enough to kind of go through the rest of the course without having to invoke these ideas of forces. Okay? So let me first of all start off with giving you a definition for a form of energy. And then we're going to try to talk about what really is energy conceptually. So the definition I'm going to give you is for kinetic energy. Now, kinetic, that's a root, that we use that root word a lot. For example, kinesthesiology, the study of how people move. Okay? So kinetic energy has to deal with motion. It is the energy associated with the movement of an object. Now we have a quantitative equation that can tell us the kinetic energy. If we know the object's mass and we know how fast it is moving, we can write down an equation that gives us the kinetic energy of the object. Now you say, where does this equation come from? Did it just like get pulled out of the sky? Did somebody sit down and investigate? And yes, this came from Newton's second law. Newton was able to take his second law, he was able to recast it. And so Newton decided, okay, well, those must be something important. I'll call those kinetic energy. He also, in the process, has some definition for what we call work nowadays. Okay, so the first thing I just want to give you is, okay, here is the equation for kinetic energy. And it allows us to get an idea about how much energy is associated with the motion of an object. I always find it funny when I'm driving down the road because, I drive a Ford Fusion. Okay? Not exactly a small car, but it's a mid-sized sedan, right? It's a family car. Okay? And I always find it funny because I'll be driving my Ford Fusion down the road at, 70 miles per hour. And then I see somebody that's driving the 6-ton, pickup truck. No offense if you're a 6-ton pickup truck kind of person. Okay? The 6-ton pickup truck driving at 70 miles per hour. And I always find that interesting because I say, really the thing that's important isn't how fast you're going, it's how much energy you have. You say, what do you mean? Well, when you get into an accident, that energy has to be dissipated somehow. You have to go from moving kinetic energy to some other form of energy. I always find it interesting because I'm like, shouldn't there be an energy limit when you're driving, not a speed limit? Okay, maybe that's just me. So how does this wrap up into our discussion about forces? Okay? And the other thing that I always find is that when we're discussing forces, you might be tempted to say, okay, well, a force is transferred from one object to another, right? I push on this chapstick thing, okay? I push on it and I transfer force from my finger to the object. And I'd say, oh, nay. Okay? I understand your desire to think that there's something being transferred from Greg to something else, the chapstick container. I understand that. Okay? It is not a force that's being transferred. Remember, a force is an interaction between two objects. So it's like, I don't know. It's kind of weird. Like, how do you transfer an interaction? Like the interaction is the thing that's happening, but there is something that is transferred. Okay. I 100% agree. It's just not a force that's transferred. A force can be applied, a force can be exerted, but a force cannot be transferred. Okay. So, what is transferred? Okay. So we go back, a net force acting on an object changes an object's speed or direction, right? This is straight out from Newton's first law. Okay. Number one. The second idea, we just gave you a definition for kinetic energy. What's the observable for kinetic energy? Yeah, the speed of the object. Okay? So we have the second thing. A changed speed indicates that an object's kinetic energy has changed. Right? If I apply a force on an object, I can change its speed. Because I observe its speed changing, I can infer that the kinetic energy of the object has changed. So what have I actually transferred to the object? Energy. Good. So the idea is this. Forces transfer energy. I'll say it again. Forces transfer energy. So how energy is transferred is through these pushes and pulls. What is being transferred? Energy. I guess an analogy would be something like this. If I think about Greg's bank account, okay, you can think of various ways that Greg's bank account can be interacted with, right? You have a debit charge that comes in, or you have a check deposited, right? Or maybe you have a bill that gets paid, or maybe your paycheck comes in. Okay? These are all different interactions with Greg's bank account. Okay? What is being transferred? Yeah, money. Okay? So the same idea goes on here. It's that forces do the transfer process, but the thing that actually goes from one object to another is the energy. Okay? Okay, so we've got some energy comments here. Okay? The first thing I will say is that energy is a zero-sum game. What I mean by that, zero-sum games are games that always have a winner and always have a loser. No ties involved. So this is a zero-sum process. If one object gains energy through an interaction, then another object must lose it. Okay? You cannot, just get more energy for nothing. Okay? So some examples of zero-sum games, things like musical chairs, things like the lottery, right? In order for one person to win the lottery, there has to be other people that lose. Okay? Musical chairs, the same thing. Right? So energy cannot appear or disappear. Okay? This is the number one rule. If you see an increase of kinetic energy in one location, there must be a decrease in energy somewhere else. Okay? Similarly, if you see kinetic energy decrease at one location on one object, there must be an increase in energy somewhere else. Okay? So that energy doesn't disappear. It can, however, change forms. Okay? So you can't cause it to disappear, you can cause it to change forms. And there will be a couple of other forms of energy that we're going to need to talk about at some point. The first one's coming right up. Okay? So first idea, kinetic energy. Okay? Energy associated with the motion of the object. Okay? So I have a different question for you. Okay? So we're going to consider this. I have a ball here. Excuse me, I'm just getting my screen up so I can see myself. I have a ball here, okay? And what we're going to think about, thought experiment, we are going to think about throwing the ball up in the air. Okay? Oh, I know, fascinating, right? Throwing the ball up in the air. Okay, there we go. Question for you. The instant after the ball leaves my hand, okay, does it have kinetic energy? Yeah, good, right? A similar question, as the ball, right after the ball leaves my hand, is the ball moving? Survey says, yes, of course it's moving, Greg. It is moving upwards. And because I see it moving, it must have some kinetic energy. Remember, we're going to take that observable and relate it to an inferred quantity, kinetic energy. Okay. Good, so that's the first question. Okay. As it leaves my hand, it has some kinetic energy. Okay, you ready? So here's the question. When I throw this ball and it's at the highest point, okay, right here, see if I can do it again. Okay. What can you tell me about the kinetic energy of the ball? Yeah, you got it? Right at its highest point, the ball momentarily stops. Right? And so because it momentarily stops, that instant that it hits the highest height, it's momentarily stopped, it's not moving. What's the kinetic energy? Well, if it's not moving, the kinetic energy must be 0. Right? It stopped. Okay? So here's the question then. Where did the energy go? Remember, our energy rule says energy can't disappear. It can't appear. It can change forms, that's fine, but it can't just disappear. But now we have an example, non-zero kinetic energy when it leaves my hand, no kinetic energy when it hits the highest height. So where did that energy go? Yeah, you probably already know where it's going. We'll keep going. Keep that in mind. We'll come back to it. Okay? A different question for you. So first of all, where did the energy go? And second of all, will the ball get the energy back? Survey says, well, if I throw the ball up, it momentarily stops, but then after that instant, yeah, it starts falling back down, right? You have a stationary object. There is a force acting on this object, namely gravity, good. And so the object will start moving downwards. And now because the force is in the same direction as the motion of the ball, it will start speeding up again. So yes, the kinetic energy disappears for a moment, but then it comes back. The ball gets that energy back. Okay, another question for you. Oh yeah, okay, we said where did it go? Different question for you. Okay. How about this? If I throw the ball faster, okay, so instead of throwing it so it stays on screen, what happens if I transfer more energy to it? In other words, instead of this much energy, I'll transfer that much. Oh, sorry, that much. Okay. Question. What happens to the maximum height of the ball? Yeah, right? If I give it less kinetic energy, the maximum height is low. But if I give it more, it goes higher. Okay? That's going to be a clue. Okay? So let's go ahead. Let's get an idea. We'll answer our question now. Where did the kinetic energy go? Okay? We'll say we have not taken into account all of the forms of energy that are possible, right? For right now, we are only dealing with kinetic energy. Kinetic. But the energy rule says it can't disappear, but it can change forms. So we are right now changing the form that the energy is in. Namely by this, I shouldn't say we, I should say the Earth. Right? As the ball moves upwards, there's a gravitational force on the ball by the earth. That gravitational force transfers some of the kinetic energy from the ball. And so the ball slows down. Okay? Now, we already discussed the ball isn't moving at the peak, so 100% of its kinetic energy has been transferred elsewhere. You say, where? What's interacting with the ball? Yeah, the earth. Okay? So somehow the earth is storing that energy. And I should be more specific. I said, say the combination of the earth and the ball have stored the energy somehow. Right? It's transferred it from kinetic into another form of energy. That form of energy has the potential of giving back the energy to the ball. And so I will call it potential energy, and it's associated with the gravitational force, right? The gravitational force is transferring the energy from the ball. So we will call it gravitational potential energy. Okay. Next question, what's the observable? How do you know if an object has gravitational potential energy? Just like kinetic energy, there's an observable associated with it, the speed. What would be the observable for the gravitational potential energy? Yeah, remember? Yeah, the observable is the height. You get a different idea. Say I take this ball and I drop it from shoulder height. The instant before it hits the floor, the ball will be moving at some speed. It will have some sort of kinetic energy. Now, if I drop it from above my head, will the ball have more or less kinetic energy than if I had dropped it from the shoulder? Say more, right? It's going to actually be moving faster the instant before it hits the ground, which means it has more kinetic energy, which means this situation must have had more stored energy in it, okay? More gravitational potential energy. Okay? Yeah, let's go back to the banking analogy. Okay? So we could think about the idea, we could say, okay, we have two different accounts where money can be stored. Okay? We have our checking account, we have our savings account. And do you know, well, first of all, money doesn't grow on trees. Okay? That is the analogy statement for saying energy cannot appear or disappear. Okay? You don't just instantaneously get money. Okay? It has to come from somewhere else. So now our idea here, we have two accounts, and you know that if I transfer money from my checking to my savings, I haven't really lost any money. It is all still there. It's just in different accounts. Now we will do the same thing. We are going to do the exact same thing, except instead of money, we're going to think of, let me get to a different color here. We're going to think of energy. That's a terrible color. Let's find a different color here, or I could just do this in post. We're going to think about energy. Right? That is the currency that inanimate objects are dealing with. And instead of a checking and a savings account, we'll call it the potential energy account and the kinetic energy account. In other words, I can take my energy and transfer it to the potential energy account. I haven't lost any energy. It's just gone to a different form, a different place. Similarly, I can transfer it back later, right? The nice thing about gravitational potential energy is you could transfer it back later. It is, they sometimes say, recoverable. So I have a question for you, okay? So I've got a bar graph, and let's consider this throwing process for a second. When I throw the ball up and it comes back down, and I want you, go ahead, fill out the bar graph. I want you to give me a visual representation of the kinetic energy of the ball at 4 different locations. Excuse me, the kinetic energy and the potential energy of the ball at 4 different locations. Okay? The instant after it leaves my hand, I want it halfway up, I want it at maximum height, and I want it halfway down. So go ahead, take a minute, fill out the chart, give me an answer. You got it? Yeah, good, good, good. Pause the video if not. Okay, so let's go ahead. Well, if it's just thrown, and let's make the approximation I'm throwing it from the ground. That's fine. So if it's just thrown, okay, you'd say that the majority, all of the kinetic energy is in kinetic energy. Okay. Now, I understand if you're saying, okay, well, you're throwing it from waist height and you put a little bit of gravitational potential energy. Okay, that's fine. But the idea is most of the energy is kinetic energy. It's in the kinetic energy account. Okay. Well, how about halfway up? Okay. Halfway up, is the ball still moving? Yes. Okay. So there must be some kinetic energy. Is the ball above the ground? Yes. So there must be now some gravitational potential energy. Okay. And we could have a debate about how big each bar should be and yada yada. You could actually figure it out. Okay. If we really wanted to, we could figure it out. That's okay. We're not gonna, don't worry about that. Okay. But the thing I'm looking for is to make sure, say if I ask this on a problem somewhere, I would make sure that the kinetic energy bar graph should be less than what you originally drew here. And your potential energy bar graph darn well better be larger than what you drew. Okay? And, okay, so that's number one. The second thing that you should be cognizant of is that if I could visually stack these 2 bars on top of each other, I should get the total energy, right? That's the idea that you can't just introduce new energy, you can't remove energy. This amount of energy should stay the same. Okay? That visually would be that these 2 bar graphs darn well better add up to the total energy. Okay? Well, at max height, we've already discussed, it's no longer moving. So the kinetic energy account better be empty, and all of the energy is stored as potential energy. Last one, halfway down. What can you tell me about the speed of the ball when it's halfway up as compared to when it's halfway down? Yeah, it should be the same, right? I mean, it's moving in opposite directions, but the value should be the same. You say, why is that? Let me ask you a different question. Halfway up, it's at some distance above the Earth. Halfway down, it's at the same height above the Earth, which means the gravitational potential energy better be the same. Well, if the gravitational potential energy is the same for halfway up as versus halfway down, then the kinetic energy better be the same. And so whatever you drew for the second graph darn well better match what you drew for the 4th graph. Because from an energy perspective, halfway up and halfway down have the exact same energies, the exact same division of the energies. Cool? So I'll put this in here, gravity. The gravitational potential energy depends on the distance between objects. Okay? If you increase the distance, then you increase the stored gravitational energy. Okay? So near Earth, I'll give you the equation. If you're dealing near Earth, like a ball, right now I can figure out how much gravitational potential energy it has by applying the equation mgh. M representing, as you know, the mass. Okay? So that M is the same in Newton's laws, it's the same in kinetic energy. M is mass. Okay? G is what we call the acceleration due to gravity. Okay? If you drop this ball right here, it increases in speed by 10 meters per second every second. So second 0, nothing. Second 1, it'll be moving at 10 meters per second. After 2 seconds, it'll be moving at 20 meters per second, and so on and so on and so on. Okay? So it's a constant. Okay? Sometimes you'll hear me refer to it as little g, not to be confused with big G. Okay? Not to be confused with homie G. Okay. H, as we've already said, the observable for the gravitational potential energy is the height, the distance between the two objects. So here I mean H to represent height. I before E except after C, unless it sounds like A, such as in neighbor or away. Height. That just looks weird. Okay. Good? Okay. So I will leave it there for the energy discussion. Okay. We have two forms of energy, kinetic energy and gravitational potential energy, and we have the observables associated with those, namely the speed of the object and the height above the surface. Okay. We will then use energy at various points as we progress to talk about other phenomena. Some of the other energy that we're going to talk about is the energy of light. Yes, light carries energy. Okay. And I'll give you the observable right now. The observable would be the color, or if you prefer, the frequency. Okay. We will also talk about energy of microscopic particles, of atoms, okay? Rather than of entire bulk objects, we will talk about the energy associated with the atoms that make up an object. Okay? So I'll say energy of atoms. And the observable there is what we will call temperature. Okay? And then we will also use these energy considerations to hypothesize that there must be other forms of energy that we haven't been creative enough to understand yet. And in fact, our knowledge is so lacking that sometimes we just simply refer to it as dark energy. Energy, we know it has to be there based on our rules for energy, or we think they should be there based on our rules for energy, but we haven't yet figured out what exactly it is. What is the observable? Okay. Our dark represents our lack of knowledge about what it is. Okay? And that, of course, will take us to the latter half of the course, probably the last week, to be quite honest. Okay? You ready for the ride? We've got our models in place. We've got a good way of discussing interactions between inanimate objects. And this will allow us to start understanding, having a better understanding of what's going on in our universe. So we'll now take a slight byline and discuss some other thing, light, which I've already mentioned here. Okay? So hey, thanks for joining me for the ride. Keep up the good work. Ask questions, be diligent. If you have questions about this stuff, please come and ask me and we'll work through some of it. So, hey, I thank you for your attention. Keep up the good work. I'll see you next time.